In the past couple of sections of this module, we've seen how the number of electron groups around a central atom dictates the bond angles around that atom. In the reading and practice problems, we've looked at 6 different molecules. We'll look at these molecules again as prototypes of the different kinds of shapes that are present in molecules that follow the octet rule. An important point to make is this. When we talk about the shape of a molecule, we'll have a word or phrase that describes where the atoms are. Yes, lone pairs can affect the bond angles, but we're not describing where the electrons are. We're describing where the atoms are. When we want to determine the shape of a molecule, it's important that we are able to draw the Lewis structure correctly. If we don't, then all of our shapes will be wrong too. We then count the number of electron groups around the central atom. This number correlates with bond angles in the molecule. VSEPR theory tells us that 2 groups around a central atom will try to get 180 degrees apart. We've used a circle to represent the central atom and lines to represent the electron groups. The circle does not mean oxygen. 3 groups will go 120 degrees apart, all in the same plane. 4 groups will go 109 degrees apart. Drawing this in 3 dimensions can be somewhat challenging. Solid lines represent electron groups in the plane of the screen. The dashed line shows an electron group going behind the screen, while the wedge coming out at us represents an electron group in front of the screen. Let's start with 3 molecules, each having a central atom and 2 terminal atoms. Our first example is carbon dioxide. We show the Lewis structure with 2 double bonds. We've left off the lone pairs on the oxygen atoms since they do not affect the shape of the molecule. Only lone pairs on the central atom are important in the shape. The 2 double bonds constitute 2 electron groups. We know that 2 groups result in 180 degree bond angles. The Lewis structure, as drawn, shows the shape of the molecule. Since all 3 atoms are in a line, the name we give to this shape is linear. Our second example is sulfur dioxide. The Lewis structure shows a single bond, double bond, and lone pair around central sulfur, or 3 electron groups. The Lewis structure is incomplete, as we have left off the oxygen lone pairs and formal charges, but these do not affect the shape of the molecule. 3 electron groups result in 120 degree bond angles. We can redraw the molecule to better show the shape. Notice that this molecule is not linear. We will call it bent. Our third example is water. The central oxygen has 2 single bonds and 2 lone pairs, or 4 electron groups. The predicted bond angle is 109 degrees. Again, the structure can be redrawn to better show the shape. This molecule is not linear, so we call it bent. Notice that when you have a central atom flanked by only 2 terminal atoms, the shape will either be linear or bent. Bent molecules occur when the central atom has 1 or more lone pairs on it. Our next 2 examples contain a central atom with 3 terminal atoms. Sulfur trioxide is shown, again without formal charges or lone pairs on terminal atoms. The 2 single bonds and 1 double bond constitute 3 electron groups. 3 electron groups give 120 degree bond angles. In this case, all 4 atoms are in the same plane, so this is a planar molecule. We call it trigonal planar since the plane has 3 sides. Ammonia also has a central atom surrounded by 3 terminal atoms, but there is a lone pair on the nitrogen. Nitrogen has 4 electron groups, leading to 109 degree bond angles. We redraw the structure with the dash and wedge bonds to show 1 hydrogen on the left and 2 on the right. One of those is coming out of the screen while the other is going behind the screen. The 4 atoms are not in a plane, but rather define the corners of a pyramid. The shape is trigonal pyramidal, since the base of the pyramid has 3 sides. We can redraw the sulfur trioxide structure using the same dash wedge scheme to show the difference between planar and pyramidal. Notice how sulfur is in the same plane as the oxygen atoms, while nitrogen is above the plane of the hydrogen atoms. You should practice drawing structures like this, as it takes a while to get used to. Our final example is methane, CH4. The 2-dimensional Lewis structure shows 4 electron groups. We would predict 109-degree bond angles. Notice how the Lewis structure is deceiving in terms of shape. We've drawn the structure planar, but we need to know the 3-dimensional shape is different. We redraw the structure, showing the more realistic shape. This is reminiscent of ammonia on the previous page, except there is a hydrogen atom on top instead of a lone pair. Because of the difference, we need to use a different word or phrase to describe this shape. We call the shape of methane tetrahedral.